Okay, now we're going to move into chapter 5. We're going to jump right into 5.2, which is called Verifying Trigonometric Identities. The material from 5.1 we'll just kind of bring up as we go, so we don't officially need to do 5.1. Okay, so it's easy just to do examples to explain what's going on. It says verify the following trigonometric identities. 1, 2, 3, 4, 5, 8 of them. So we're going to do 8 of them. All right, so what is an identity, first of all? I mean, you've probably seen this phrase in previous courses. For example, if I said 5 plus x is x plus 5, right? That's an identity because no matter what number you plug in for x, this side will equal that side. That's an identity, okay? And for example, if I said x squared plus 1 is 7x, notice this is not an identity because if I plug 0 into both sides, I get 1 equals 0, and that's not true. So this is not an identity. An identity is an equation that's true no matter what you plug in for x, as long as everything is defined. So this begs the question, if this is not an identity, what x's do make this true? That's when you would solve the equation, right? So if you have an identity, there's nothing to solve. Everything works as long as everything is defined. Okay, and we've had identities in this course already. Okay, so the first example says prove this is an identity, meaning if you plug a theta here, here, and here, and a theta here, as long as everything is defined, which for some values a cosecant won't be, but if both sides are defined, you will always get the same answer on both sides. That's what an identity is. Now, what's the procedure for proving an identity is true? You start on one side and work your way to the other. It's not solving an equation and doing things to both sides, even though some books say to do that. Okay? So my guiding principle in proving an identity is true is I typically pick the side that's more complicated in some regard, whatever that means, because it's easier to destruct than it is to start with something simple and construct, because you don't know what to do, it's so simple. So with that in mind, I'm not going to start with the right-hand side, because what are you going to do with cosine squared? It's so simple, you wouldn't even know where to begin. Whereas this side is a little more complicated. There's more stuff going on, right? So the first thing you should do, right, that's the problem. Write down the side you are starting with so the reader will know. The point of an identity is to convince somebody that these are equal. Okay, so write down, because some problems, both sides may be equally complicated, and some people may start on the left, some may start on the right. So you should tell your teacher, or the reader, what side you're working on first. So I've written down the left-hand side. Now we're going to do stuff to this. Don't write equals cosine squared. I don't know that yet. That's what I'm trying to convince somebody. So what could you do to this to start making it look like cosine squared? Well, every once in a while you look and see where you're going. That may give you ideas. I don't know that this, looking at cosine squared gives you any ideas. But what's something you could do? Even if you just had no clue what to do, what's something you could do? Well, you could distribute the sign, right? So if I could distribute the sign, that might get you somewhere. Okay, so that's sine cosecant minus sine squared. Now sometimes it may get worse before it gets better. Keep that in mind too. Okay, now another strategy that sometimes gets you somewhere is, notice on the left I have two different trig functions, sine and cosecant. On the right hand side I have a single trig function. Now it doesn't match, so that thinking doesn't help. But you have two on this side and one on that side. A strategy that is sometimes helpful is change everything to sines and cosines. So if you have an expression with 6 trig functions, you can write all 6 trig functions in terms of sine and cosine. You go from 6 different trig functions to 2. And then sometimes things cancel or subtract out. So that's my strategy here. I'm going to change everything to sines and cosines. So I already have sines here, so that's no problem. Now how do you write cosecant in terms of sines and or cosines? Cosecant is 1 over sine, isn't it? So now I only have an expression with sines in it. And notice what happened here. Sine times 1 over sine, the sines cancel. I get 1 minus sine squared. Okay? Sometimes you just go with your gut. Okay? I always have students that say, how did you know what to do? Sometimes you don't. You just have to try something and see what happens. Okay? You're not going to see 8 steps ahead. I have students say, I don't see how I'm going to get to there. Don't worry about getting to there. Sometimes it's just a matter of trying something. And then you say, oh, okay, well, what can I do here? Oh, you may not realize in the beginning that those wind up canceling and give you a 1. You just have to get going and try. Okay, now notice where we are. This looks a whole lot better than that, okay? But we're not quite there, okay? Now, something you need to keep in mind is we had 3 Pythagorean identities. For example, one of them, which you should have memorized, is sine squared theta plus cosine squared theta is always 1. That's the way I have this one memorized, right? Sine squared theta plus cosine squared theta equals 1. This is an identity. No matter what you put in for theta, this will be true, okay? Sine and cosine are never undefined like that, so that will always be true. You can make new identities from old ones. For example, if I subtract sine squared from both sides of this equation, I get that. So if this is true, and vice versa. So I've made a new identity from one I already knew. But notice what I have. Cosine squared is 1 minus sine squared. That's what this is. 1 minus sine squared is that side, so it must equal that side. And that's what I was trying to get to, so we're finished. So I started with the left-hand side and did stuff to it, and I got to the right-hand side. Now, you may say, well, how did you know to do this? Okay, whenever I see, remember, in any Pythagorean identity, we had a trig function squared, and a 1. When I see any 2 of those things in an expression, I try this little procedure. So notice here I had a 1 and a sine squared. I know I have a Pythagorean identity with a 1 and a sine squared in it. So I wrote that one down and said, how do I get a 1 minus sine squared? Subtract sine squared from both sides. Now, just because it looks like, if this had been 1 plus sine squared, this wouldn't have worked, because to get that on the other side, you have to subtract, not add, okay? So just because you have 2 things doesn't mean the Pythagorean identity is going to help. And remember, the second one was 1 plus tangent squared theta is secant squared theta. So if I say a 1, a tan squared, and a secant squared, if I see any 2 of those, I try that same sort of thing with that identity. And then the other one's 1 plus cotan squared theta is cosecant squared theta. Okay, so just keep that in mind, because it's not going to just leap off the board at you sometimes. So that's the first one. Okay, the second one is this one here. Secant theta plus cosecant theta times quantity cosine theta minus sine theta is cotan theta minus tan theta. Okay, so we want to start on one side and work our way to the other. Another motivation, besides which one's more complicated, is sometimes you look at this side and you just don't have any idea where to begin. But the other side, you do. You have an idea of something to try. So start with that side and see where you get. So I think here, okay, that's the original problem. So I'm going to start on the left just because it's more complicated. There's just more going on there. Plus, I have an idea of something to try. Right? Equals. So I'm starting with the left-hand side. Again, do not copy the right-hand side. I do not know they're equal. That's what I'm trying to show. Okay? So I have 1 of 2 things in mind to do here. Do you have 2 different things in mind you could maybe do? Of the 2 ideas, whatever I do first, I'm going to do the other one second. So it might remind you of this. Notice what we do here. We did a multiplication, and then we changed everything to sines and cosines. Notice I have 4 different trig functions here. So this one it may be a good idea to change the sines and cosines, because then you're down to 2 trig functions. Or you might consider multiplying all that out, foiling it out. And that's what I'm going to do. It doesn't matter which order. I'll just multiply first, because that's what I did here. It doesn't matter. So if I FOIL this out, you get secant theta cosine theta minus secant theta sine theta plus cosecant theta cosine theta minus cosecant theta sine theta. Again, on your paper, you should put this all on one line. I just ran out of room. All right, let me check myself. Secant theta cosine theta, secant theta minus sine theta, cosecant theta cosine theta, minus cosecant theta sine theta. Okay, I'm good. Okay, now again, I still have 4 trig functions, different trig functions. So why don't I change everything to sines and cosines? So secant is 1 over cosine times cosine. Secant is 1 over cosine times the sine. Okay, so now I'm continuing here, plus cosecant's 1 over sine times cosine minus 1 over sine times sine. Okay, So again, secant 1 over cosine, secant 1 over cosine, cosecant 1 over sine, cosecant 1 over sine. Now let's do some simplifying. Remember I mentioned before, sometimes it gets worse before it gets better. Look how nasty this looks. There's a lot going on compared to the original, but I have 1 over cosine times cosine. That's 1. And then let me just write that as a single fraction. That's sine theta over cosine theta, this one. Here I have cosine over sine. I'm just multiplying fractions. You can think of these as over 1, right? Think of the cosines over 1, right? And then here I have, I did that one. And then here, 1 over sine times sine is 1, so I have a minus 1. And notice the 1 minus the 1 drops out. Okay, so that's good. But what else is going on? Well, what's sine over sine theta over cosine theta? Sine theta over cosine theta is tangent theta. So this is negative tan theta. And then cosine over sine is cotan theta. That's quotient identity we did before. And notice this is the right-hand side. So we're done. So just using we used 3 ideas here, didn't we? Well, 4. We multiplied. We changed everything to sines and cosines. We multiplied fractions. And we used our quotient identities. And notice here we multiplied. We used multiplying fractions. And we used a Pythagorean identity. Those 4 or 5 things I mentioned use over and over and over again in problems in this section. Okay? Now you may not use them in every section. Notice here I didn't use quotient identity. Here I didn't use Pythagorean identity. But these same sorts of things we do over and over and over again in this section. Okay, let's do the next one. Oh, this is dirty. Okay. It's 1 plus tan squared theta over 1 plus cotangent squared theta, and we want to show that's equal to tan squared theta. Okay. Now again, please don't get creative with your algebra. Don't make up things. For example, you cannot cancel the ones. You're adding, right? You can only cancel when it's something times something times something times something divided by something times something times something. Right? So if you're adding, if you have a plus b over a plus c, you cannot cancel the a's because the a's are being added to something. Okay? You don't have something times something, you have a plus something. Okay? So don't cancel if you're not allowed. Okay, I think it's obvious I'm going to start with the left-hand side. It's a lot more complicated than the right-hand side. Okay, so I'm going to start with the left-hand side. Okay, now, something should be leaping off the board at you at this point. 1 plus tangent square. Remember I mentioned the Pythagorean identities before. I know there's an identity with a 1 and a tangent squared. And now the question is, does it match? It actually does. I don't have to do the rearranging I did before. 1 plus tangent square is secant squared. That's a Pythagorean identity. I don't even have to rearrange. Same thing here. 1 plus cotangent squared is cosecant squared theta. Right? Those are just straightforward memorizing. You have to know all your identities, that your basic ones to use here. So I'm using a Pythagorean identity and a Pythagorean identity. Here I use quotient identity and quotient identity. Okay, and reciprocals. I use reciprocal identities. Secant was 1 over cosine. So you have to know all your identities very well. Right? So we still have a quotient, something over something, but notice we got rid of the plus. Right? So everything, this is secant times secant over cosecant times cosecant. Now you can't cancel right now, but if things matched up, we could. Now we're trying to get to tangent squared. Well, if you don't have any other ideas, what's something you could do? Let's change it to sines and cosines, right? So what's secant squared in terms of cosine? That's 1 over cosine squared. Remember, secant, cosine are reciprocals of one another. And cosecant squared is 1 over sine squared theta. So I know it looks worse, but I have a fraction divided by a fraction. How do you divide fractions? You leave the numerator alone, 1 over cosine squared. To divide by a fraction, you invert and multiply. So this is times sine squared theta over 1. So right, I've inverted that and multiplied. So notice what we get when you multiply fractions, you just multiply across. That's sine squared theta over cosine squared theta. Make sure you can do operations with fractions, addition, subtraction, and multiplication and division. Remember, to multiply fractions, you just multiply across. to divide by a fraction, you invert the denominator and multiply. Now, what's sine squared over cosine squared? Remember, sine over cosine, we used it here. Sine over cosine is tangent, so sine squared over cosine squared is tangent squared, and that's what we were trying to get to. Notice I just went with my gut. Pythagorean identity was obvious here. I mean, I recognize that right away. And I was like, how do you get a tangent squared? It's not obvious. But what could you do? Well, change the signs of cosines. As soon as you do that, have a fraction and a fraction. It makes sense to invert, multiply, and then combine. And you realize there's sine over cosine, so you got your tangent. So sometimes you just have to go with your gut. That was obvious to me. This may not be so obvious, but it's something reasonable to try. Going from here to here is obvious, here to here to obvious, and then that's no problem, okay? So sometimes you just go with your gut, and it works out. Okay, let's do the next one. Oh dear. Oh. Okay, so the next one says cosecant x minus sine x is cosine x cotan x. Yeah. So if you try to argue which side's more complicated, it's 6 of one, half a dozen of the other. Here it's the difference of two trig functions. Here it's the product of two trig functions. I mean, those are both equally, same level of difficulty as far as I'm concerned. So, do you have an idea of what maybe you could do with one side or the other? See, here I think I would change the signs, because cosecant x is 1 over sine. And here I think that I change the sines and cosines. But you're going to get a sine and a cosine. So from that point of view, I'm going to start on the left, because when I change it, I only have one trig function. Okay. Now, like I said, you could start over there and try something, and then if you get stuck and you don't know what to do, fine, try the other side. Okay? You're not going to get these on your first try a lot of times. You're going to start, like you do some work and you may go off on a weird direction and it turns into a giant mess. Fine, backtrack and pick up where you left off, okay? You're not going to get these on your first try, okay? These take practice. Okay, I'm not saying these are easy. Again, they look easy when I do it because I've done them 100,000 times. I know, I have an idea of what to try sometimes. Okay, so I'm starting with the left. Let me rewrite cosecant in terms of sine. That's 1 over sine minus sine. So now I only have one trig function to mess with. Okay, now what's the problem here? This is a difference, and this is a product, right? It's something times, I don't have a plus or a minus here. So we want to get rid of the subtraction somehow. Well, how do you do that? Well, let's subtract the fractions, okay? So you can think of this sine x as sine x over 1, right? I want to subtract fractions. So how do you subtract fractions? You need a common denominator. What's the least common multiple of sine x and 1? Well, it's sine x. So the least common denominator is going to be sine x. Well, I already have a sine x here. I'm going to leave that alone. I don't have to do anything to that because I have sine x. Now, how do you get a common denominator in a fraction, right? For example, if you had 1/2 and you wanted to get the common denominator of 6, what do? You multiply by 3 over 3. That'll get you your 6. And notice you're multiplying by 1, so it doesn't change the value of the fraction, it just changes the appearance. So if I want to get a sine x in the denominator, I need to multiply by sine x. But you can't just do that. That changes the value. You have to put sine x in the numerator. So notice I'm multiplying just, not the whole thing, just this part. I'm multiplying this part by 1, so I'm not changing the value, but I'm going to change the appearance. So I have 1 over sine x minus sine squared x over sine x. Again, to multiply fractions, you multiply across. Now I have a common denominator. So to subtract fractions with the same denominator, you leave the denominator alone, and you subtract the numerators. Okay. Now notice that it looks worse than where we started. But we have a single thing now, okay? Can we cancel the signs? It'd be nice if we could, but you cannot. You're subtracting. It's not something times something divided by sine. It's 1 minus sine squared. It's a subtraction. You cannot cancel. Well, what could you do with that? Well, do you have an idea? Hopefully you do, because I see in the numerator, I see a 1 and I see a sine squared. Those are two things that are part of a Pythagorean identity. So off to the side, because most professors wouldn't need to see this work because they would know what you did. Sine squared x plus cosine squared x is 1. How do you get a 1 minus sine squared out of that? Subtract sine squared from both sides. This is the exact same one we did before, right? Subtract sine squared from both sides, that's what you get. So 1 minus sine squared is cosine squared. So this is cosine squared x over sine x. Okay. Notice when we don't have a quotient, there's a cosine, right? So it looks like we're getting close. Let me continue up here. So I need to get a cosine and I need to get a cotangent. So it makes sense. Instead of cosine squared, let me steal a cosine from that. So the cosine x, say over, well, yeah, I'll just say cosine. You can put it over 1 if you want, but the cosine times cosine over sine. Now, do you understand what I'm doing? Right, again, if that's over 1, right, that's cosine squared over sine. It's the same thing. But see, here's where it's helpful to look at where you're trying to get to. I didn't really use that up to this point, not really. But see, I need a cosine. I have a cosine squared, so let me pull one off, okay? So there, I've got my cosine to match, but then notice what I have here. I have cosine x. What's cosine x divided by sine x? That's a quotient identity, cotan x, and there we go. So notice that did help me. Looking what I was trying to get to, I need a cosine times something. I don't need cosine squared, so let's pull a cosine off. That still leaves me a cosine. And oh, lo and behold, that's what we need. Right? So sometimes looking at what you're trying to get to will help you decide what to do. Like here, I need a cosine times something, so let's steal one. And then you see what's left. Oh, that's cotan, we're finished. Okay, so I'm going to do the second half of this section in a separate video.